Hi everyone, we will discuss the paper on LDA UCID. These are our team members. Imagine we are making an animal classifier, and initially we had images of dogs and cats and the corresponding labels as well. So we successfully deploy an animal classifier based on dogs and cats. Now we want is, can the model successfully classify foxes and wolves as well, of which we do not have any data. We assume these animals as classes and that they are part of a Gaussian distribution. So we have x naught and y naught as the initial label dataset, and then we train our model f theta by minimizing the empirical risk factor, which is just a loss function. And now we have been supplied with t unlabeled datasets from x1 to xt, and our goal is to update the source trained model f theta using unlabeled data while avoiding some key challenges. As you can see, we are continuously changing our domains. Then we can expect fairly that the distribution is shifting from original to some other places. And also, as you can see that, for example, at time t, we are learning this model, then there is highly chance that the model can tend to forget the initially trained parameters. So first I'll give you the general solution. So you remember the dogs and cats training data, label training data set. Let's say that is D naught, and that is separable in a higher dimension space phi naught. And we apply the classifier H naught in this dimension. As we are given new inputs throughout the space to get the final p space, now we have k classes. Initial distribution is the summation of k Gaussian distributions, and then we find the map estimate to be this. Notice that all the results here are in phi space. Now let's talk about at any time t. Okay, now we would say that this pjt is the internal distribution in the embedding space z, and this zit is just a random drawn from this distribution, and the model assigns some y I t for this embedding, and only for those in which the is like it's more than a threshold. Now this would generate the random sample dataset DTP, and just tend to minimize the following loss function. Now the first term is the loss term for the classifier HW, which ensure the model can generalize well on the pseudo dataset ZP. The goal is to make the prediction of the ZT like match the YT, pseudo labels YT. Okay. The second term is basically minimizing the SWD distance between the target domain prediction and the original label generated by the internal distribution. What about the mitigating of the catastrophic forgetting? For this process, we need to have buffer memory, a small set of representative samples from each class, and they are very close to the GMM mean of that class only. We add these two terms, basically having the terms like the buffer domain. The second term prevents the forgetting by retaining on buffer data, while the fourth term consolidates the internal distribution across all the domains. Now coming to the algorithm, so initially we had the input of the label dataset, and we had the model created by minimizing the EMR function. Now the internal distribution estimation is basically done by the map distribution, and we obtain the parameters, and we set the memory buffers for each class. Now what we do for time 1 to time t, where the input is basically the unlabeled dataset dt, is basically we had this dt, and we also add the memory buffer in the encoder to get an embedding in the z space, and then we classify it shown over here, and then we just do the minimization operation for this to learn the new model. So the model is now updated, and the memory buffer is updated for the next input, and hence completing the algorithm. The results on when let's say we take this one. Now there were 3 data sets for digit recognition task. If we see here, it trained S first, then M, and then U. So just as S was trained, there was a huge bump, there was a jumpstart performance. And now, when the M input was given, there was a slight decrease, but it was relatively stable. So we can say the catastrophic forgetting was nearly zero, and if we compare it with classical UDA models, it outperformed or nearly matched the classic UDA methods. With that, we conclude